I want to show you
Very
that all what we have talked about has real effect. It is relevant in the real world. And the example that I want to show you is the French presidential elections, which is one of the large-scale elections that is done by the method of plurality voting. Actually, the French constitution says that it is plurality with runoff. And that means the following. There are a number of candidates. Usually in French presidential elections, it's 15 to 20 people who run for president. Then every French citizen can cast one vote to each of them. Well, one vote to the preferred candidate. And that would be plurality. Plurality would then simply count who has the most votes and he will be the president. No, it's a little bit more complicated, because it says that, all right, if in this first round, one candidate receives the absolute majority of votes, which almost never happens, then he will be, or she will be, the president. Otherwise, and this is what always happens, the two candidates who receive the most votes go to the so-called runoff, where then it is a decision between two candidates. Now, please think with me a little bit about it. It sounds like a good idea, right? Because, why? Because in the second stage, you do have only two candidates. And we already know that two candidate elections are something very simple, and there are good methods to decide in two candidate elections. And so the idea is, or one could phrase it in that way, the idea is to somehow reduce the number of candidates in the first stage in order to have this good case of two individuals on which we have to vote. But the problem is that plurality with runoff is in some sense even worse than plurality. Why? Because in the first stage, this process of reducing the candidates, that has an enormous potential of manipulation, and not only manipulation, in fact, of selecting not correctly, in some sense, the two candidates that go to the runoff. And this is actually what often happened, well, at least sometimes happened. And I think the most pointed case was 2007. And I want to talk to you about this 2007 case. The following happened in the first round in April 2007. Nicolas Sarkozy received 31% of the votes, Ségolène Royal 26, François Bayrou 19. Then there was Jean-Marie Le Pen, the father of Marine Le Pen, with 10%, and all other candidates received less than 5%. Well, this is a typical picture, actually, for French presidential elections. There are, of course, many of these, say, up to 20 candidates. They receive very little number of votes. But you see what is happening here. The two with the most votes, that is Sarkozy and Royal, go to the runoff, and the runoff was won by Royal, was won by Sarkozy against Royal, I'm sorry, with 53% of the votes. Now, you can say, well, that's okay. That's at least what happened in the second round is okay. But the point is, it was not okay who went into the second round. Why? Well, because these polls before the elections, they constantly reported that Bayrou would have beaten either Sarkozy and Royal in a pairwise comparison, right? So because Sarkozy was, of course, the right-wing candidate, Royal was the left candidate, and Bayrou was in the political middle, which means that every supporter of Royal at the left would have still preferred Bayrou to Sarkozy, and every supporter of Sarkozy to the right would still have preferred Bayrou to Royal. So in a pairwise comparison, Bayrou had beaten both the right and the left candidate, because Bayrou was one of these middle candidates, right? So in fact, in some sense, Bayrou was the compromise candidate, actually the Condorcet winner even, right? So the polls indicated that Bayrou was in fact the Condorcet winner in this election. But you know, this is exactly what happens when there is polarization, but at the extremes, there is a little bit more than 1/3 of the votes. Then it is the extremes against each other, whereas many people would have preferred, at least as a compromise, the middle candidate. So you see, it's not that the middle candidate was preferred as first choice, right, by many. No, only 20%. But many of these 26% would still have wanted to have Bayrou rather than Sarkozy, and the 31 who were for Sarkozy would have preferred Bayrou to Royal. And therefore, it's not a good idea to let the two extreme candidates, well, relatively extreme. I mean, of course, Jean-Marie Le Pen was far right, but he was not really a contender here. Okay, anyway, so this led researchers to rethink about the election system in France and of how to elect the French president. And there are still current initiatives to reform the electoral system. For instance, there are mathematicians, Michel Balinsky, who died recently, unfortunately, and his collaborator, Rida Laraki. They have proposed another voting method, the so-called majority judgment method. And the basic idea of the majority judgment method is not to vote for candidates, but to give them grades. And this is a very interesting idea, actually. And the idea is as follows, and you can see this here in a table, and this table resulted from a field experiment just after the elections in 2007. Namely, what happened was each voter should not give one vote to one of these candidates, but to say that how well he would find this candidate on a scale of excellent, very good, good, acceptable, poor, to reject. And there was also the possibility to simply say, I don't give a score. Now, just a second, before you think that, oh, this is like Borda, it is completely different from Borda. Why? Because what is done then, the candidate with the highest median grade wins. This is a very different idea from summing over the, I mean, you could also say, all right, excellent means 5 points, very good, 4 points, good, 3 points, acceptable 2, and so on. And then you sum over the points. No, that's not what is done here. It is not Borda rule. It is the candidate with the highest median grade who will be declared the winner. Now, how does this work? Look at the table, and this is actually the figures that were observed. So Bayrou, for instance, got the grade excellent from 13% of the population. He got the grade very good by 30, good by 25, and so on and so on. So these numbers here should sum up to 100. I hope they do, right? 100%. So for every candidate, every voter has to give one of these grades, or simply say nothing, no score. And the same for Royal. Here are the figures for Royal, then Sarkozy, and so on and so on. Now, for each candidate, you determine what is called the majority judgment. The majority judgment for Bayrou is good. Why? Well, because more than 50% of the population said Beirut is good or better, and more than 50% said Beirut is good or worse. Okay, that's you can see that immediately, right? Because you have 43 or 45% above and some smaller number below. So this must be the median grade in the sense that that more than 50% are better or equal, and more than 50% are worse or equal. And for Royal, also the grade good is this. For Sarkozy, also good. For the rest of these candidates, the majority judgment or median grade was worse. So it is only a question between these three. No surprise here, of course. But now what you can do now is you can, of course, put a plus or a minus depending on whether the number of people who had a grade better than the majority judgment, better than good, is greater, or worse than good is greater. And here, for Beirut, it's the only candidate who received the median grade good, and more people saying he's even better than that. Whereas for Royal and Sarkozy, more people would say, no, Royal is worse than good, and Sarkozy is worse than good. Okay, I mean, of course, for this now you have to compute these numbers. You have to see that this is really true, what I'm claiming. But if you sum here, 16 plus 12 makes 28, 38, 39, and you have something like, it's a knife edge case for Royal, right? But for Beirut, you have 43 say he is better than, 44 even, he is better than good, and only some 22, 26, 28% say he's worse than good. You get Beirut as the unique winner, as it should have been. Well, you could argue as it should have been. You could also try to argue against. But then, is the problem solved? We simply need to go from rankings to gradings and say how good we think people are, and we have solved the arrow problem, or we have found a way of electing that solves all the problems that we have. No, unfortunately not, because also this method has a problem, and the problem is very simple, and here it is. Suppose there are three voters and now only two candidates, and you would think, well, with two candidates, we know there is not a problem. We should simply vote by majority or take the Condorcet winner. But I mean, with two candidates, the Condorcet winner is something very simple. It is the candidate who receives the majority. But now suppose that one voter says A is excellent, B is very good. One voter says A is acceptable, B is good. And one voter says A is poor, but B is to reject. Now, the median grade for B, look at it, very good, good to reject. The middle grade is good. The middle grade for A is excellent, acceptable, poor is acceptable for A. So B wins the majority judgment, right? The median grade for B is good. It is only acceptable for A. But now this is not the right choice here in this example. Why? Because look at this voter. The voter to the left says A is excellent and B is very good. And the voter to the right says A is poor, but B is even to reject. Now we have a clear majority of two voters who would rather have A than B. Of course, this is a misanthrope here, this voter. He says all candidates are bad. And this is an optimistic guy. And she says, oh, all candidates are good, or even excellent, very good, right? So in a sense, what you could argue here is this voter and this voter are not speaking the same language. But then you have to worry about the properties of the language, and that has been done, of course, also by Balinsky and Laraki. Can you say something more about the distribution of grades in the population that would prevent such a case to happen? Yeah? Of course, you can do that, but the example clearly shows that the problems are not solved by this method. Unfortunately, it would have been good to have a method that solves the problems, but majority judgment has its own problem. Let me close this overview actually with the following advertisement. In 2011, the British said that plurality rule was not the right thing to do. And there was a referendum to go from plurality rule in England to another system called alternative vote. Now, I want to explain this to you in a little bit detailed, because now there is a political economy element here, and I wanted to also talk about political economy with you, mostly tomorrow, not so much today. But here is the problem. In England, the parliament, the seats in the parliament are determined within each district in the country simply by plurality, right? Exactly as in the French presidential elections, there are a number of candidates in each district. And the candidate who receives the most votes, the plurality winner, gets the seat in the parliament. Now you can imagine what happens if the population is divided as you see here, right? There are 30% of coffee drinkers, and they would like to have coffee, 30%. So each, you see here 10 items. So each coffee mug stands for 10% of the people. Each beer cup also stands for 10%. So you have in total 10 here. 2 plus 2 is 4, 5, 6, 7, 8, 9, 10. So you see here the 100% of the population, 30% coffee drinkers, and 70% beer drinkers. The problem is the beer drinkers cannot coordinate which pub to go. 20% want to go to the Queen's Head, 10% to the Green Man, 20% to the Castle, 20% to the Red Lion. These are all, of course, pubs, right? Whereas these 30 want to go to the coffee shop. Now, if everyone votes for the most preferred alternative, then plurality gives you coffee, okay? Although 70% of the population would have preferred to go to the pub. And that's a problem of plurality voting. And that's a problem in England, actually, where the seats in parliament are not representing the proportion of party supporters in the population. And you see why this can happen, right? I mean, these 30% are just the plurality here, because the beer drinkers cannot find a common compromise. Okay, all right. So this was the advertisement actually to abandon this system of plurality voting, which in Britain has a different name in Britain. It's called first past the post, but this is simply plurality. And this was an advertisement by the supporters of the alternative vote, AV. And so if you know a bit English dialect, then you know the pun here, because you have to read this, of course, like, let's have a beer. And that's how some English people would say if they want to have a beer. Okay, anyway. All right, let me stop here my slides, my introductory slides. So let me suggest now to have a small round of questions. And during that small round of questions, I will look now at the chat window, and you can ask me questions in the chat window, but if you prefer, or you can use either method. I mean, either you use the chat window, I'm having now an eye on it, or you just speak up and unmute your mic if you wish to do so. So during you thinking about if you want to ask a question, let me tell you more now about the course. So that was the overview, but my hope, of course, was that already in the overview, you understand the problems and why it is important to think about elections, and that you have already an idea of the controversy between Condorcet and Borda, and that these Condorcet or methods that are based on binary comparisons of alternatives, they work in a very different way from the methods that, like the border count, that sum points and choose the candidate with the most points. These are really two very different classes of voting rules. And the question which one to take or to choose is a very deep question. And my hope is that I have conveyed a little bit of the depth of this question, but to repeat it, suppose you are in a situation where you have three candidates. Let's say a right candidate, a middle candidate, and a left candidate. Now suppose that a little bit more than 50% vote for the right candidate, and the rest is somewhere in the middle. Or I'm sorry. Let's start with a simpler case. Suppose that among the three you have an almost equal distribution, so that everyone has around 30%. And suppose that there is reason to believe that preferences are single-peaked, right? As in the political spectrum, you could assume, which simply means that those who prefer the right candidate would still want to have the middle rather than the other extreme. Okay, let's assume this. Now, if you have, let's say, uniform distribution, 1/3 of the population for each candidate, then there is a good reason to choose the middle candidate, right? Because of this single peakedness property, that candidate somehow is a compromise. That was exactly what we argued in the French presidential elections, right? I mean, the middle candidate is a compromise. He's still preferred by the extremist on the one side to the extreme candidate of the other side. And that's a good reason for choosing the middle candidate. Now, but this continues to be a good argument, even if you change a little bit the proportions of the voters. But plurality, notice, is completely insensitive against this. If I put a little bit more mass on one voter, then plurality immediately chooses this candidate just because there are some epsilon in addition. Now, that's why plurality is not good. But the argument goes even further, namely in the moment where one candidate hits the 51% limit, then Condorcet would always say, we have to choose this candidate because now it's a Condorcet winner, even if it's not in the middle. So let us now suppose you put all the mass to the extremes. There is still this middle candidate, but now all the mass of the voters goes from the middle candidate to the extremes. Now suppose you have 50% here and 50% here. So you have a completely split society. 50% are left extremists, 50% are right extremists. What should you choose? Well, perhaps still the point in the middle. Why not? And now assume you put 50 plus epsilon on one side and 50 minus epsilon on the other side. Now Condorcet says, well, now you have to choose 50 plus epsilon. But it's not clear that this is really true. Should you really do that or not? And I think this is a deep question. This is something that actually perhaps not even social choice theorists can answer alone, but you have to have a very general analysis of such situations. But unfortunately, this is yet exactly the situation that we find in some countries where the societies become more and more polarized. Well, sometimes also without a middle candidate, as in the US. I mean, the situation in the US is more or less like 50% would like to have weapons everywhere and no abortion and so on and so on. And the other 50% are completely against it. So so I think this is a worthwhile topic to study. What can prevent polarization and which electoral systems can lead to less polarization in the long run? Okay, if there is no question, I will then simply go on in my presentation, and I want to, yes,
if you don't mind.
Of course.
I have a question that sometimes if we, for example, think about France elections, then we see that the candidates with high anti-ranking, so there are a lot of people who do not like them, but maybe there is like some private interest in this hate to this candidate. So don't you think that in the for society, it would be better to sometimes to choose the person who is not supported by a lot of people, but so he has high anti-ranking like Trump, but maybe he can change the society to the better, and there are the most people who support him. So like in plurality, he gets the most part of votes.
But the problem is when, like in plurality, he gets the most votes, but a majority thinks that that candidate is terrible. Wouldn't you think that this is a problem? I think Trump is a good example, right? The supporters of Trump are the loudest, okay? And perhaps even the plurality supports Trump, whereas the rest of the American population says, well, I don't know what is really a good candidate, but what I know is that Trump is the worst one. Right? This is more or less, remember, this is the situation in the French, this example that I gave you from the French Academy of Science, right? Where you had 4 voters supporting candidate A, right, who was then the plurality winner, and you had 5 voters who thought that A is the worst candidate. And now my question to you is, I didn't understand your argument exactly. Wouldn't you think that the majority thinking that this is the worst of all candidates, isn't that a good argument not to elect him?
But maybe, yes, it's a really good argument and really strong argument, but at the same time, we should understand that this majority who try to elect him, maybe it has the different view to change our society, and maybe it's quite a good view.
Well, but how? Yes, but this is somehow hoping, what you're arguing is you're hoping that the candidate will do something that even the others will find good at some point. But this is a kind of dynamic argument that you're making. You say, well, perhaps this candidate will change the society in a good way. Now, the question is, do the voters now believe that he will do so? And if a majority believes, then they will vote for him. But if they don't believe, so you somehow introduce an element of you knowing better what this candidate will do than the voters. Okay, you understand? Do you understand
Yes,
my
I understand.
point?
Thank you.
Yeah. Okay. Okay, more questions.
Well, thank you for your first part of lecture, and I want to ask you, in your opinion, is distribution on the scale of right and left still relevant? Maybe right on migration and left on education and health and many other questions. Thank you.
Yeah. Okay. This is a completely fair. I mean, as far as I understand, you hint at the following problem. It is too simplistic to capture everything in one-dimensional spectrum from left to right. And I completely agree. I mean, at least since the rise of green parties in Europe, there is a second dimension, like how much do you want to care about environment or versus technological improvement and immediate profit from certain technologies. So as you know, in Germany, we decided to abandon nuclear energy in favor of other forms of energy. And this is actually at a high cost, right? Because we are choosing technologies that, at least at the present moment, are not as profitable as other technologies. And now the point is that this is a different dimension than the traditional left-right spectrum. As you can see in Germany, there are now several places where at the state level, the conservative, that's the traditionally right in this political spectrum party, is having a coalition with the Greens, which were first thought of being rather left, but actually green politics is simply orthogonal to the usual left-right axis. So if you want to hint at the fact that this is a simplistic way of looking at things, I completely agree. On the other hand, what you can do is you can try to generalize this notion of single peakedness, as I said, from a line perhaps to a two-dimensional thing and have similar results than the median voter theorem. Does this answer your question?
Thank you. Yes.
Very good. Good. Are there further questions? You can also use the chat. I will now show my next set of slides. And let me tell you the following. I would be very interested in, so now I will be a bit more formal, right? So far, that was quite informal description and more based on examples. What I want to do now is I want to introduce to you really the formal analysis of this. And I want to formulate the arrow theorem so that we all know really what that is about. This is the fundamental starting point for so many discussions. And in the end, perhaps today or at the latest tomorrow, I would like you to give me some idea in what direction you are more interested in this formal and more detailed presentation style or in this informal style. And then I can try to adjust a little bit there. So let me now go to this next slide set. Just a second. Here it is. Now I open that. So hopefully now you can see this slide set, and I will do the full screen mode. So do you see in full screen mode social choice theory, Arrow's theorem, and social welfare functions?
Yeah, yeah.
Yes.
Very good.
Very good.
Very good. So this is then the next topic. I want to give you the impossibility theorem. But I will start with a motivating example. Here is again an example. Suppose that there are 5 communities, A, B, C, D, and E. And they are of equal size. They have the same population. And they want to decide where to build a public facility. Let's say a hospital. Well, let's say a public swimming pool or a hospital or a movie theater that would be used by all of them. And the problem is this is in the mountains, or for some reason there are only the streets which you can see, right? This graph that connects A, B, C, D, and E, this graph is simply the net of roads that connects these communities. And actually at W0, there is simply, how do you call that? When the way splits in one or the other direction. So here you can decide when you travel from C, at this point you have to decide whether you want to go to E, to the left, or to D, to the right. But this is not a community itself. It's just a point where the ways split, right? A bifurcation. Okay. Now, the distances is given here. And the question is where to build the facility. Notice that if you simply assume that preferences are very simple, the further away the facility from your own place, the worse for you. Then C is the Condorcet winner. How do you see that? Well, compare C with everything to the right, and then you will know the communities A, B, and C will prefer C itself to any place to the right of C. And the communities E, D, and C will prefer C to any place on this street and any place on this street. So you see, if you do pairwise majority comparison between C and any other location along the road, C will win. It's a Condorcet winner. As you know, a Condorcet winner does not always exist. But now the question is, would you choose C always? Why not? I see someone not being okay with that. Do you want to tell me why you're not, why you don't agree to C?
There is a problem of justice, let's say.
Yes, exactly.
And I mean, I would prefer W0 point. I mean,
exactly.
No one gets the priority.
Yes, very good. That's exactly correct. Now that was Mikhail's example was, suppose it's a hospital. Well, then, of course, we need to worry about the maximum distance that some community has to the hospital. Suppose we build the hospital in C. Of course, the people A, B, C, they are very happy, but those in E have 8 kilometers to travel. Now, suppose that you have an emergency case where it is really important that you arrive at the hospital in short time, then E have an extreme disadvantage. So you could have other principles like the Max-Min principle. It's related to the name of Rawls. John Rawls proposed to look at those people in society who are worst off, to those who have the least welfare, and try to improve them first before improving others. And this would yield exactly this solution as you suggested, namely W0. That minimizes the maximal distance that one community has to the hospital, namely 5. And you cannot do less than 5, as you see here, because the longest path is 10 between B and E. This is 10 kilometers, and half of it is 5. So the maximal distance cannot be lower than 5. And that would be a good reason to choose W0. But notice now, we do something that we should think about. Namely, we compare the distance to the hospital of different communities. Now, if we have distance, this is a very natural thing to do. But in general, we do not have this measure of distance, right? It is not clear what does it mean to look at the worst of individual. For this, we need to know how worse is an individual off. And this is exactly what is the topic of the second part of this slide set. If we can do interpersonal comparisons, then something new happens in this theory. But for the first part of this slide set, I assume that we cannot do interpersonal comparisons. I cannot say, that's the assumption here, that one person with one candidate is better off than another person with another candidate, right? It's not clear how to make these comparisons. If you have streets, yes, then you could say, well, we can make this comparison simply by asking how far away. That is a measure of how well you are off. But we will in the first part not do that. And what means not doing that? Well, that means we will only look at the so-called ordinal preferences. Okay, so here is now the framework that I want to present you. R here is simply the set of all possible rankings of candidates, okay? And we allow indifferences, and we allow that for some candidates, a voter says, oh, they are equally good. That we can allow, this is no problem. That is then called a weak order, in contrast to a linear order where you have a strict ranking of all candidates. Now, this symbol here with the index 1 means this is the individual preference ordering of voter number 1. And now every voter submits her preference. So you have a profile of individual preference orderings for each voter 1. This is this profile here. And a social welfare function simply takes such a profile and tells you what is the social preference that corresponds to this profile of individual preferences. Okay, so this function is called capital F. And now in this framework, I want to formulate the arrow conditions. Remember, the first one was unrestricted domain. In the following, I call it U for unrestricted. And it simply says that this function F should be defined on the set of all logically possible profiles of individual preference orderings. Technically, they should be reflexive, transitive, and complete binary relations. Okay? That's also called a weak order then. And notice I am already ruling out this case of single-peakedness, right? I mean, they can be single-peaked, but unrestricted domain means, and if they are not single-peaked, I still have to be able to apply F, right? So I'm not ruling out the single-peaked case. I'm simply saying that I'm ruling nothing out, but the single-peaked case rules this out, that you are not single-peaked, right? That's ruled out by single-peakedness, and here nothing is ruled out. That's unrestricted domain. Okay, now you could do something very strange. Let's say a function that is constant, right? consider the constant social welfare function that says the ranking for the group is this ordering, no matter what the individual orderings are. That would be very strange, right? So that would mean that Sarkozy should be the president, no matter how the people in France have voted. Okay, but that's completely crazy, right? Because why is it crazy? Now, suppose W0 is the best alternative with respect to that ranking, then this would be the alternative selected. But now imagine a situation where every voter in France said, wait a minute, we prefer another candidate, let's say it's X. Then if you have a constant social welfare function, you would still select Y0, and this is completely crazy, right? Why? Well, because this would violate exactly this condition down here, weak Pareto. So weak Pareto simply says, if all people, all voters prefer X to Y, now even strictly, right, then the group must prefer X to Y. So this would violate this condition. So fixing the social ranking would not satisfy this condition, and therefore fixing the ranking without consulting the voters is not a good idea. Okay, so this is weak Pareto. Okay, this is the second condition then. Let's come to the third condition in Arrow's theorem, dictatorial social welfare function. Here is a proposal that would satisfy unrestricted domain and weak Pareto. I do simply the following. I fix some agent K, let's say Mikhail is this agent K. And if we collectively decide on something, I ignore all of you. I only ask Mikhail, what do you think? What should we choose? And then we choose this. Is this good? Well, in the case of Mikhail, it is good, of course, we know, but that is by pure chance. We cannot write in the constitution that Mikhail should determine the outcome. And it could happen that Mikhail has a different opinion from all of us, right? And the question is, should we accord this? Probably not. So the no dictatorship means at least there must be at least some situation in which we do not do what Mikhail wanted to do, okay? It's okay that if many times our choice is the same as Mikhail's most preferred choice, that's okay. But it cannot always be Mikhail's preferred choice that what we choose, because that would mean no matter what we think, Mikhail decides. That is called a dictatorial rule, right? And we want not to have a, right? We want to have a democracy. That means no single individual should always determine the result. Okay, so that's no dictatorship. Do we have a method that satisfies unrestricted domain, weak Pareto, and no dictatorship? Yes, and we already know this method. It's border score or border count. Okay, if we have a finite set of alternatives, let's do candidates, let's say M candidates, then every voter allocates M points to his best, M minus 1 points to the second best, and so on. Now, if you have indifferences, you should somehow solve this. This is only a technical problem. Then the border score of each alternative is simply the sum over all these points it receives from each agent, and the social preference ordering is determined according to the border scores. An example, we had already examples. Let me just give you another example here. One voter says X better Y better Z better W and so on. Let's take border scores. Border score for X is 4 plus another 4 plus 1 is 9. notice that 1, 2, 3 is the name of the voter, is not the number of voters, but the name of the voters, yeah? Y gets 3 plus 3 plus 4 is 10. Z gets 2 plus 1 plus 2 is 5. And W gets 1 plus 2 plus 3 is 6. So the social preference, the preference for this group of 3 voters is Y, 10, then X gets 9, then W, 6, and the last is Z gets 5 points. All right. Now, suppose that the agents receive the information that Z and W are not really an option. Or in other words, suppose that notice, voter 1 and voter 2 have X and Y on top and Z and W on the bottom. It is only voter 3 who has W before X, right? So he has W on rank 2 and X on the last place. Now suppose there comes the information that says, oh, W and Z are not really, we cannot elect them in this, right? So that would change 3's preference, saying that actually W and Z are the 2 bottom candidates, whereas because they cannot be elected, it's only about Y and X. Now notice that W and Z in the border ranking here will not be elected, right? They are the 2 worst candidates. And now the voter 3 changes her mind about the ranking of X and W, right? And nothing else has changed, but now the border score for X is 11, whereas the border score for Y is 10, right? Because X moved up here in voter 3's ranking, now X becomes the border winner. Or in other words, because W went down the ranking, X becomes the winner, okay? This is something strange. Why? Well, because notice that W and Z were not even contenders. The question was always about, should it be Y or X? And now an information about W changes our view about X against Y. In other words, W is an irrelevant alternative in the decision between X and Y. And this is formalized in this arrows independence condition. It's sometimes called independence of irrelevant alternatives. I prefer to call it binary independence. And now this is something I want to read with you and to really understand the essence of this condition. Consider 2 situations, and we considered just 2 situations. Remember, one where the W was at place 2nd for voter 3, and one where it was below. So 2 situations. This is the first profile. This is the second profile with a prime. But now fix 2 alternatives, X, Y. If you find that the voters who prefer X to Y here are exactly the same voters that prefer X to Y here, and the voters who prefer Y to X also. So preference for X over Y does not change from this profile to this profile. Other things change, but not the preference between X and Y. For no voter, for every voter, nothing changes in the preference between X and Y. Then, for the group, nothing should change. So if you apply this social welfare function, F, right, this one, which represents the group preference, then the group preference should not change between X and Y, of course, only. Okay? So this is the arrow condition of binary independence. And then we have the theorem now, and now we have really a mathematical theorem which we can prove if time allows. No, probably not. But now we have a mathematical statement, namely, if the set of candidates has at least 3 elements, then every social welfare function that satisfies condition U, weak Pareto, binary independence, is dictatorial. That's the arrow theorem. I want to give you an idea of the proof, please, because the proof is so clever. The proof is based, now it's mathematics, and perhaps for those of you who are not trained in mathematical proofs and logical thinking, don't worry if you get lost now a bit. I want to briefly go over it so that you have seen that there is really a mathematically exact argument here. And the argument works as follows. Let's call a group to be decisive for X against Y if for all profiles, whenever the members in the group L, all voters in the group, when they prefer X to Y, then the group prefers X to Y. Of course, this is given a social welfare function F, right? So I now assume you have given me a social welfare function F fixed. And I will prove to you that if this F satisfies universal domain, weak Pareto, and independence, it must be dictatorship of Mikhail. Now, of course, not of Mikhail, but of one individual, okay? And this I prove with this concept of decisiveness. So given F, I know, I mean, this is simply a definition that tells me whether a group of individuals is decisive or not. I can even strengthen the definition a little bit and call a group weakly decisive for X against Y if the following holds. If the members in the group prefer X to Y, and if all others prefer Y to X, right, then the group will prefer X to Y. Notice that from the pure logic, this is a weaker notion than this one. In other words, every decisive group is also weakly decisive. Why? Because decisiveness means no matter what the other people have as preference, the people in L can force their preference. And here it says, only when the others have the opposite preference can a group force its preference. So pure logically, this is weaker than this, although intuitively it seems to be stronger to be decisive if everybody else is against. But pure logic means that this case is subsumed here as well. Okay, good. Just for notation, I have a clever notation here. D of LXY means group L is decisive for X against Y. WD means it's weakly decisive. And D of L without any further alternatives here, without candidates, means the group is decisive for all pairs of alternatives. Now, I have two lemmata, and then we will have proved the theorem. The first lemma says, if there exists A and B such that the group L is weakly decisive for A against B, then it must actually be decisive for everything, right? So weak decisiveness for a particular pair implies full decisiveness for everything, okay? Let's postpone the proof. The second lemma says, suppose a group is decisive and the group has at least two members. Then there exists a proper subgroup that is still decisive. So now take this also as given, and if you take these two lemmas as given, we can prove the error theorem. Why? Because this second lemma gives you everything what you need. Why? Weak Pareto condition says that the group as a whole is decisive. Because weak Pareto says if everybody prefers X to Y, X must be preferred to Y for the group. But that is the group of all individuals, N is decisive. Yeah. The second lemma says if a group is decisive and has more than one element, then I can split this group into two subgroups and one of them will still be decisive. Now let's do that, okay? Then I have a subgroup of less individuals, which is still decisive. If it has still more than one element, I can even further split it. And one of the two groups, the two subgroups, will still be decisive. And I can do that until the moment where I have only one person in this group. And this is the dictator. Okay? So this is the logic of this proof. So we have to prove the second lemma. Okay? And if we have proven the second lemma, then we are done. Unfortunately, for the second lemma, we need the first lemma. Okay? So let's prove first the first lemma. Okay, here's the proof. It's not so difficult. Remember, just a second, let's go back. The first lemma says, if there are two alternatives A, B, such that the group is weakly decisive, then the group must be decisive for everything. That we have to prove. What was exactly weakly decisive? It meant that in every situation where the members of this group prefer A to B and everybody else prefers B to A, the group must prefer A to B as the people in L. Okay, that is the definition of weak decisiveness. All right, so let's go here. Choose two alternatives A, B, and two other alternatives X, Y, and assume without loss of generality that they are all different. Of course, you have to worry about the case of three alternatives, then they cannot be all different, but this is technical detail. Okay, so for simplicity here in this proof, I suppose that A, B, X, Y are all different, and that the group is weakly decisive for A against B. Okay, now the unrestricted domain condition allows me to consider the following profile. The people in L, in this weakly decisive group, they have the following preference. X is better A is better B, and B is better Y, and everything else is down here. If there are more alternatives, more candidates, they are down here. The people that are not in L have the following preference. X is preferred to A, B is preferred to Y, and B is preferred to A. And nothing else is known about them. But notice what is known is that A is preferred to B by these people, and B is preferred to A by these people. Now, since the people in L are weakly decisive, this group is weakly decisive, we must have for the group that A is better than B. Okay, the weak decisiveness of L for A against B means the group must prefer A to B. But notice that all individuals prefer X to B, X to A. Yeah. So, and B to Y. So all people here prefer X to A and B to Y. So we know by the weak Pareto condition, X must be preferred by the group to A, B must be preferred by the group to Y, and we also have A is preferred to B by this weak decisiveness. But now you see X better A better B, B better Y, so by transitivity, X must be better than Y. But notice, go back, X must be better than Y, but for these people, I know nothing about X and Y, They could have any ranking. You have to check this, of course. The ranking of these people outside L between X and Y can be anything. Okay? Only the people in group L prefer X to Y. But X and Y were completely arbitrary. So I have proven the people in group L, this group is decisive for everything, right? Because X and Y were arbitrary, and I have made no restriction to the people outside L. So we have proven the lemma. Okay, so the first lemma is proved. I suppose, to be honest, I suppose that you want to look at the proof again and perhaps ask me tomorrow questions to the proof, which is totally okay if you want to do that. Now let's go to the second lemma. The second lemma says that if you have a group that is decisive for everything, and it has at least 2 members, then there must exist a proper subgroup that is still decisive. Here is the proof. It's just as short, and then we are done for today, actually. I will finish on time, no worries. If L has more than 1 member, we can split it into 2 proper subgroups, L prime, L double prime. By the unrestricted domain condition, we can now consider the following profile. The people in L prime have this preference, A, B, C. The people in L double prime have B, C, A, and all people outside L have C, A, B. Okay? We can consider this, no problem. By the decisiveness of group L, B must be better than C for the group, because both L and L prime, they make up the group L, and they both have the preference B is better than C, right? So, of group L, we must have B is better than C. There are now only 2 cases to consider. Either for the group as a whole, we find that B is better than A, or we find that A is at least as good as B, right? These are the 2 cases. Let's assume B is better than A. Now, if B is for the group better than A, then look, only the people in L double prime have the preference B is better than A. All others say A is better than B. Now, by the binary independence, this means that this group is weakly decisive for B against A. Remember, these are the only people who prefer B to A, and still the group preference is B is better than A. So by the binary independence condition, this group L double prime is weakly decisive. But by the first lemma, weak decisiveness for some pair means you're decisive for everything. So in this case, we have found the decisive subgroup, it's L double prime. Second case, A is at least as good as B. We know by transitivity now, A is at least as good as B. We know from the beginning that B is better than C. So by transitivity, A is better than C. Now, who thinks that A is better than C? Only the people in L prime. Look, only those find that A is better than C. All other people think C is better than A. What does that mean? That means by the binary independence condition, this means that now L prime is a decisive group, weakly decisive group for A against C. But if you are weakly decisive for some pair, the first lemma said you are decisive for every pair, and now it is group L prime and not L double prime, but that's it. In either case, we have found that some smaller group of voters must still be decisive under these conditions of weak Pareto, unrestricted domain, and binary independence. And now we can make the group even smaller and smaller and smaller until only one person is left, and this person is the dictator.